Good morning. Thank you very much for the invitation to give this talk. I'm going to stand here. If I'm in anybody's way, let me know. Otherwise, it's really bad on my neck. So I'm going to talk about optimized traces for MPI and show you where we are going. Before I do that, let me introduce the key players of this game. Most of the work I'm going to talk about are done by former students of mine, Matt Ferguson, Amit Kandahar, and a chemist who works with us. We have a startup company, so they moved from the university to the startup company. And then some of my current students, Hamid Arami, and postdocs, Asahi Tomitaka, and then other students. We have collaborations with UC Berkeley, with the Connolly Group, and you saw some of the images from Professor Connolly yesterday using our particles. We are obviously collaborating with Philips, with Jürgen and Jon, and I will show some images taken with the Philips system as well. Collaborating with TU Braunschweig, with Professor Frank Ludwig and his students. And we have other collaborations as well with Roy Chantrell, who is a theorist, Professor Takemura from Yokohama, and my former student who is now a professor in China, Tianlong Wen, and a colleague of mine, Lucian Brush. So that's the people that I have to acknowledge before I get going. So very quickly, just to tell you our perspective on how we approach the MPI problem. MPI, of course, we have an AC magnetic field that excites a superparamagnetic particle, ideally speaking. And so you have a magnetization response, and essentially it's an inductive measurement. So you have essentially the derivative of the magnetization that we're interested in. And one of the ways of processing this is, of course, it's in Fourier space, that is the Phillips approach. And the other approach is to just take this very simply, plot the magnetization, derivative of the magnetization as a function of the field. And this we call essentially the response of the particle. This is instrument independent. And once you apply the field gradient, then what you have then is the point spread function. So this is the sort of what we use as a qualitative measure for the performance of the particle. So we measure in a spectrometer, we measure the derivative of the magnetization with respect to the field, and then we use that as a qualitative measure of the performance of the particles. Now, so the way, of course, you can create the image reconstruction process that we use, this is the so-called the X-space, or the approach taken by the Berkeley folks. It basically gives you the density of the particles, the point spread function, the magnetization, and the gradient and the slew rate. And then you can see that what determines the performance is really the point spread function. And here I show you our current results. The curve in orange is the curve for reservist. The one in black is for our particles. And you can see that we can get half the point spread function so we get 100% improvement. And this is, of course, where the intensity is normalized. Here is the actual intensity. So we also get probably about 6 to 8 times the signal of reservist. Okay? And in this approach, you want the narrowest point spread function to give you the optimal performance. One of the interesting things that we understand in order to understand the physical process is that if you really integrate the signal, you actually get the AC hysteresis loop. So it's an idea, it gives you a sense of how the particle is performing its hysteresis behavior under the alternative field conditions. And of course, this is the image that you saw yesterday taken with our particles shown by Steve Connolly. Now, of course, the other approach is the frequency domain approach. In this case, you have, of course, the imaging volume. You divide it into NX, NY, NZ voxels. And then in each of these, you have the harmonic signals. So you have a matrix that is the product of all of this. Plus, of course, you have 3 detectors. So you have a whole huge matrix that you have to invert. And one of the ways that one does this, of course, the way the Phillips approach is to to determine a system function measurement. And then the bottom line here is to look at the harmonic spectrum of our particles. So this was done, this was almost 2 years old data now, or 1.5 years old data, and our performance is much better. And what I want to point out is that this is for reservist, this is our particles, and you can see that we continue to have higher harmonics with our particles. This is almost up to 80 harmonics here. We have a spectrometer in my own lab where we measure it, but up to only 40 harmonics. And then you can see this is the current status, this is reservist, this is our particles, and you can see so much more significant higher harmonic content from our particles. So that's they are essentially equivalent whether you do the point spread function or the harmonic approach. But since people are doing the image reconstruction in two different methods, I just want to show how our particles perform. So of course the advantage here, of course, is the rapid scans and so on. And so this is again about a year old, measurements done with Philips, and you can see these are the phantoms, and here's the reservist, here's our particles, and you can see so much significant performance compared to reservist. And this is done the same way now at Berkeley. Again, you saw these images yesterday, and you can see this is reservist, this is our particles, and here's the recent experiment done for resolution by separations of these, and you can clearly separate around 2 millimeters with our particles, and you simply cannot do that with reservist. So this is the status. Now the question then is, so this is where we are, and so the remaining 20 odd minutes of my talk, I'll tell you how we get here. So that's basically what we have done, and so how we get here. So our approach is quite comprehensive in the sense that our goal is not just to make the tracers, our goal is to make sure that the tracers can perform in a human body. So ultimately, we want to have a clinically relevant tracer that we intend, hopefully, to take it through an FDA trial and so on. So in order to do this, we have to, so it's like what we call the sort of the particle development tetrahedron. So you have essentially on one end of the tetrahedron, you have to get the physics right. Then you have to do the synthesis, the chemistry and the biochemistry on the outside. And then you have to do the pharmacology and then translation or medicine. So we have to do this, all of this, and you have to do this in some sort of cyclic form so that you can fail at any point and you have to start all over again. And so it's not that you can just do this in a sequential fashion, but you have to do this in a cyclic form. You have to take it all the way, and if it fails, you start all over again. So that's basically our approach, and I will show you probably 5 minutes on each of these things. So the first thing is a little bit of physics. So when you have small particles, they behave up to a certain size as superparamagnetic, and then they transition to a single domain ferromagnetic behavior, and then they become multiple domain particles. And you can see that initially the superparamagnetic single domain, multiple domains, and the characteristic size for all of this depends on the temperature and the volume if you assume a measurement time of 100 seconds. If you do that for iron oxide, the the size is about 30 nanometers. Now, in practice for MPI, you not only have the temperature and the volume, but you also have a time domain. And if you include the time domain, now you have the magnetic behavior, temperature, volume, and time, then this characteristic size changes depending on the frequency. As you change the frequency, as you go to higher frequencies, this characteristic size changes from 30 nanometers to about 20 nanometers. Now, if you do that, what happens in practice, this is actual measurements done with Professor Takamura, you can actually see that instead of a DC hysteresis loop, which is a superparamagnetic loop, what you end up is an open hysteresis loop. And if you do any modeling based on superparamagnetic behavior, like the Langevin function, it's really not really valid. Okay, so that's the point here. And then, so this is the first paper published by Weissnecker and so on. And they tell you essentially that the resolution depends inversely on the gradient and as a cube of the diameter. This is all based on the Langevin function. So you take the derivative of the Langevin function, numerically integrate it, and calculate the half-width of the Langevin function, and then you calculate what the resolution is. But of course, as I just told you, in this case, you can keep increasing the particle size and expect larger and larger particles, better and better resolution. But that strictly does not happen because you no longer have the superparamagnetic behavior. The loop starts to open up. And you can see that you have this behavior, and you have to somehow accommodate this because you're ultimately looking at the derivative of this hysteresis curve. So is there an optimal size? So that was the question that we were asking ourselves. Is there an optimal size? And so we have to obviously look at relaxation in alternative fields. So we have an AC field, You have a magnetization. The magnetization lags behind the applied field, so the susceptibility has a real part and an imaginary part. You have an in-phase component and a loss component. In the ideal case, when the applied field is far less than the anisotropy field, we are in the so-called linear regime, and in the linear regime, you get this ideal behavior. You have the real part of the susceptibility, this is the imaginary part of the susceptibility as a function of frequency, and this peak of this occurs at a frequency that is inversely related to the relaxation time. So we have to ask ourselves, what is the relaxation time? And in reality, of course, when we actually make a measurement of the susceptibility, the real and imaginary part, it doesn't really look like this, it actually looks like this. So that's because obviously we are not really in the linear regime. Okay. So now we have to ask ourselves the question, what is the relaxation time? And so we have two kinds of relaxation. You heard all about this in the talks yesterday. There's a Néel relaxation time, where you have basically an unblocked particle where the magnetization rotates, and it goes exponentially as the size as the volume of the particle. And then you have the Brownian relaxation time. Now remember, all this neglects the field amplitude. Okay? So when you do that, the Brownian relaxation time depends on the hydrodynamic volume and the viscosity. And typically, since this goes exponentially, it goes like that at size. This goes linearly with size, it goes like that. And there is some characteristic size where it transitions from the Néel relaxation to the Brownian relaxation. And there is, of course, this intermediate regime where it's a combined Néel and Brownian relaxation. So that's the basic understanding if you neglect the field amplitude. Now, in our case, we cannot neglect the field amplitude because we are applying about 20 millitesla field amplitude when we actually do the measurements. If you do that, then you have to include the field amplitude. So the Néel relaxation, you saw all this very complicated sort of modeling from the Brown paper in 1963, but it can be very simplified in this very simple form, where what happens is the energy barrier there is an energy term that depends on the field amplitude. So it's a very sort of physical understanding is as you apply the field amplitude, the energy barrier goes down, and it goes down exponentially with the field. And if you now look at the Brownian relaxation, this was the original very simple term without the field. Now you can look at this in this very simple sort of model put forth by Yoshida, which gives you a very physical understanding, because now you have a torque that is coming not only but also coming from the external field, which helps in the rotation. So you have to write a torque balance equation, and the torque balance equation gives you two terms. Let's go back here. The torque balance, there is a frictional torque, which prevents the particle from rotating, is balanced by the magnetic field torque and a Brownian relaxation torque. So if you balance these things and you solve the so-called Fokker-Planck equation numerically, then you get a solution of this form, where the Brownian relaxation time now has a field component, it is modified by the field, and then you get the effective relaxation time, where both the Néel relaxation term and the Brownian relaxation term depends on the field amplitude. Okay? And if you do this, now you can calculate all of this now. So if you look at the Néel relaxation time, as you apply it to the field, the relaxation time becomes much slower, much faster, because you can see that because of the exponential dependence of the field. And in the same way, the Brownian, there is a transition which we saw, and if you apply the field amplitude, you can now put in for the Brownian relaxation time as well, and you can see now the transition changes as you increase the field amplitude. So this is for about 10 millitesla, and now when you have a 20 millitesla, you can see now that essentially the Néel relaxation dominates, because now the field amplitude is in the exponent, and therefore you essentially get the Néel relaxation time dominating at these large field amplitudes. So Néel relaxation dominates, and then in order to test this argument, we tested our particles in frozen environments where we do not have the Brownian relaxation, and this is in DMSO, and you can see, for example, there is no change when the particle is free and when it is frozen. And so we know now that the Brownian contribution is quite small, and not only that, we also see that the signal is linear, even in the frozen environment. And that gives us just an ongoing work. We are trying to do this and understanding how the freezing mechanism itself works. and is linear over a broad range, and I think this has some very positive implications in terms of molecular imaging, stem cell tracking, and so on, because the Brownian relaxation provides very little contribution to the signal of these particles. So now that's the physics. So basically the bottom line of all of this, the take-home message is that we think somewhere between 25 and 28 nanometers is an optimal size to make the best MPI particles that will give you a very strong nail relaxation even in applied field amplitudes of 20 millitesla. So now we go to the chemistry a little bit. The chemistry, if you look at the iron-oxygen phase diagram, it's actually, this is the equilibrium phase diagram. And you can see there are multiple phases of iron and oxygen here. And you may, in what we do is a non-equilibrium synthesis, kinetically driven synthesis. And when we do those kinds of synthesis methods, you can get particles that look like this sometimes, which look wonderful, or you can get the same particles that look the same, but they are very, very different. For example, this particle turns out to be wustite, which is antiferromagnetic, and this particle is magnetite. And you have particles that look so different, and then what you have to do is very rigorous characterization of the structural phases of these particles. So we, of course, do that by a number of different methods, by X-ray diffraction, electron diffraction, Raman spectroscopy, and so on and so forth. So we also have been doing some extensive modeling, thermodynamic modeling of the kinetics of nanoparticle growth. And the bottom line here, which was just recently published in Journal of Colloidal and Interface Science, shows that when you have smaller critical nuclei, you get very nice size focusing. And in order to get the really nice size focus growth, you have to maintain a high monomer concentration, but smaller than the nucleation rate, so you have the particles growing uniformly without nucleating. So that's the essential chemistry of what we do. And so we can do very nice size control by growing the particles in organic solvents. Just so that we drive the point home, here's a picture of reservist. This is what reservist looks like, and this is what our particles look like. And we not only have particles, we can control the size very, very accurately. Here's 14 nanometers, 18, and you can see they are self-assembled over large areas. And in order to get self-assembly, they have to be highly monodispersed. So they have very monodispersed size distributions, and you can see this is 14, this is 18, 23. This is roughly what we believe are the ideal particles for MPI. And you can see these 27 particles, they are spherical, and you can see they're very high quality particles. Okay, so let's say what's the current status of our particles. So these are the particles, these are about 26.6 nanometers. High resolution electron microscopy shows that the particles are defect free. We can measure their particle size from magnetic measurements. They're roughly about 25, 26 nanometers. Their hydrodynamic size, and we'll talk a little bit about that in a minute. So the particles, the other important point from a commercial point of view is that we no longer make particles in very small quantities. In the chemistry lab, we used to make 50 milligrams and so on. Now we have scaled up the synthesis to 3 grams per batch, and we are still working on scaling this to up larger quantities. And you can now see when we scale up very large areas of highly uniform particles, and this is what we believe are our first preclinical traces. And again, the performance is shown here. This is, of course, the point spread function. This is the harmonic spectrum. So the reason we get such uniformly distributed particles is because we grow them in organic solvents. And now we transfer them from the organic solvents to the water phase. We then coat them with a second sort of functional polymer on the outside. And one of the important things to recognize when we do this is its long-term stability in both, first in water, then in other biological medium. And when your coating is not very good, the hydrodynamic size changes with time. When the coating is good, you see that the hydrodynamic size does not change with time, and it is stable in various biological medium. And then, of course, we're also looking at shelf life, and I'll show you other data. So the surface coating, colloidal, and the MPS signals, this is what we do. Because we make it in organic solvents, you have one layer of surfactant around it, and then we put a second surfactant to transfer it, or second organic polymer to transfer it to the water phase. And again, here we are interested in stability. We are using a PEG-based coating on the outside, and depending on the PEG density and chain length, the stability varies. You can expect that the interparticle interactions depend on the density of the PEG coating and also on the chain length of the PEG coating. And we can see, for example, when we have a large PEG chain length and high density, it is very stable with time, and you do not get particle agglomeration in water. And Amit Kandra will talk about this later in the same session. One of the things that we are working with Frank Ludwig, just a plug for the work we are doing, one of the things that we have noticed is sometimes when we transfer from the organic phase to the water phase, two particles are coated as one. And one of the signatures of two particles being coated as one is in this AC susceptibility measurement. You can see this particular peak. So we are now starting to pay attention also to this peak in the AC susceptibility measurement that allows us to see how the phase transfer takes place, whether we get a single particle coated and transferred or it's multiple particles. Shelf life and stability, it's an ongoing experiment. It's right now at 3 months, and we can see that our particles are stable when they are stored in the refrigerator at 4 degrees centigrade. When they are stored at room temperature, they're not stable. When they are stored in the freezer, they're not stable. But at 4 degrees centigrade, they are stable for 3 months, and the experiment is still going on. And these are the measurements, of course, at day 0, 3 months later, day 0, and so on, at the refrigerator, and you can see there is no change in the magnetization or in the point spread function over time. The last 2 or 3 slides I want to show you is on the biology side. The first experiment is on blood circulation time. So we have some preliminary results. Basically, tail vein injections. The particles are injected through the tail vein. They are drawn out through its retroorbital blood draw, so we draw it out of the eyes. And then we monitor the blood. We measure the iron content or the particle content. And it's very important to distinguish the iron content and the particle content. If they are only in the particle form, you will continue to get an MPI signal. If they are just in the form of iron, then you don't get an MPI signal. So this is measurement taken with the MPS spectrometer of the blood drawn at different times. So we actually get a continuous MPI signal from the particles circulating in the blood. And currently our results are that we get 20-minute circulation in rodents, in mice. That's a half time. The circulation is much longer, but the half time is 20 minutes. So 20 minutes with about 400 beats per minute compared to the human heart rate, it's very optimistic for the possibility of delivery by injection and without requiring a catheter. So it looks very promising from that point of view as well. The second important point from the biology point of view is the biodistribution. So where does it go? How does it go? And we find, for example, we are very pleased to find that there is no presence of the particles in the kidney. It's mostly in the liver and in the spleen. And this is measurement done over a week. And we have some more recent results done over a month. And it shows that the preliminary results, these are also all ongoing experiments. The results show that it gets metabolized in the iron mechanism in the body, and then it goes in and then it comes out and so on. And this is something that we are now doing with greater sensitivity and detail. The other thing we have also done is to make our traces have multiple contrasts. So both, of course, they have MPI contrast, they have MRI contrast, and we have also put in a functional optical near-infrared fluorescent tag on these. And then we can also use that to understand some of the biodistribution as well. So, and these, I just want to very quickly mention, we have looked at the linearity of these signals and so on, and that's a completely different experiments. But the bottom line from here for this discussion is that we can take these optically tagged traces, put them in the mice, look at the biodistribution, but we can also resect various organs, the liver, the spleen, the kidneys, the lungs, and so on, and then look at them in greater detail to see where exactly are the particles going. And if you do that, for example, in the liver, you see the particles are uniformly distributed, but in the spleen, they are distributed in what is called the marginal zones or the red pulp region of the spleen. So this is again an ongoing experiment to see where exactly are the particles going, what is the true biodistribution of this. Okay, so I think my time is almost up. I told the chair that I will do it 27 to 28 minutes, so it's 28 minutes. And so this is what I started with. This is the slide I started with. I told you that we are doing this sort of cyclic approach to look at the particle development in a holistic, comprehensive way, and I hope I convinced you that this is exactly what we are doing. And so I'd like to now finish with 2 slides. One, of course, to acknowledge all the people that have worked, the funding agencies. It's like a little movie now. So it shows you all the people, and it's getting longer and longer every day, so I can't do it on one slide, so I have to do it like this. And then I want to show you that this is a large area, and you see these little dots, These are particles that are in a crystallographic orientation, which are highly diffraction contrast, with a strong diffraction scattering. And so if you tilt the particles, they will tilt in such a way that certain particles will come into a diffraction. So what I want to show you is our particles are extremely well behaved. So if you tilt it properly, at some times they do this. Thank you very much.
Thank you, Professor Krishnan, for this very interesting keynote speech. I think it became clear that he is an expert in designing and manufacturing nanoparticles for MPI, and he has done pioneering work. Thank you also for staying in time. And are there some questions?
Yes. What about the thickness of the... So we're measuring the hydrodynamic radii. They are typically between, we can tune them between 40 and 60 nanometers. And that's again, Amit will talk a little bit about that because that's very important, as you know, in terms of biodistribution and so on. So we are really working on that. Okay. Ingo.
So
26, 27, yeah.
So what happens if in the future for clinical demonstrators we need to go down to say 4 or 6
Yeah, it won't change very significantly, but it's in that region. It won't be bigger because you see as you change the field amplitude, you're probably going to a minor loop, right? And so the minor loop, essentially the slope is very, very poor. And if the particles are also, if they're ferromagnetic particles, it also depends on the particle orientation. And if you go and look at the old Stoner-Wohlforth models and so on, it all depends on particle orientation. And if you average the particle distribution, the directional average, then you lose a lot. So, it's a little bit more, we are working on it. We just built our spectrometer to be able to go to higher frequencies. And so we are starting to now work on, after seeing, we were going to go to 100 kilohertz, and after seeing that you guys are now going at 100 and higher, so we're going to redo our spectrometer to sort of match your frequencies, and then we'll do this again. Yeah.
Other questions,
yes,
please?
Very, very nice paper. Just a question about the tag. You mentioned 20 kilodalton tag is probably the best for circulation and coating. Do you have experience with smaller one? I mean, years or in the clinic, the preferences for smaller sized tags?
We have data. I showed you 5 kilodalton and 20 kilodalton. And Amit will talk about this in more detail in his talk later on in the same session. Yeah. Yes.
Have you experienced the biodistribution for lymph nodes? Because that would be
No, we would like to, we will, after hearing the talks here, we will actually look at that as well. But I think they're probably really too small for us to work on mice with the lymph nodes. Yeah.
What, the Pison?
Yes, please.
Thank signal and perfectly demonstrated that the ground motion is not so important. But my question relates to the temperature. Since we are working at 37 degrees in the body, it may change. So do you have any data on this temperature effect?
No, we have there is a whole different area where I actually use the particles for heating purposes. So I have done work in that area for 10 years before this. So there is a whole, it's a somewhat more involved discussion. Maybe we can do this at some other time.
The other question is on the infrared tracer. How do you couple the infrared tracer to the iron oxide particle? Is it included or is it attached? Or
It is actually an amide bond on the surface. Yeah.
So,
Yes.
one last question, please.
What do you think about the multiple subcore composite particles like the micromodifier? What do you think they're going?
I don't know. You have to ask them. You have to ask them. I can only tell you what they're doing.
So there are no more questions. Again, thank you, Professor Krishnan,
Thank
for
you
this
very
nice
much.
talk.